Yeah, we got that going. All right.
Now we have to listen again. Can we get screen cap?
Probably can't hear it.
Yes,
Yeah.
we can.
You can never hear
We
it.
can do screen cap.
All right. So we're going to talk a little bit about the second derivative, and the second derivative is the rate of change of the first derivative. So I'm going to sort of write it a little bit sloppy the first time, and then I'll put it all together in a neat way the second time. So to go back to something that we probably feel comfortable and confident with, we know that if the function is increasing, that's the same as saying that the derivative is positive. You all right with that? Good enough? All right, here's the analogy. If everything you know about the relationship between the function and its derivative is true, the same holds for the relationship between the derivative and its derivative, or the second derivative. So, if the first derivative is increasing, that correlates to the second derivative is positive. Is that okay? And likewise, you could probably tell me, look, if the first derivative is decreasing, that is the same as saying that the second derivative, or the rate of change of the derivative, is negative. Is that all right? Do you want to ask a question? I know we're just sort of writing now, and we'll get to the point where that feels very natural, but right now, is there anything that doesn't feel natural or intuitive about those last two statements? Okay. A quick divergence to talk about notation for the second derivative. You could have a function like position, and then you could also have a function, let's see, you could have, how do I want to write this? You could have the velocity function, which we know is the derivative of position. Okay. You could also write that as dy dt using Leibniz notation, right? If the function is y, it's a change in y over the change in time. Is that okay? Acceleration, to put it in a physics context, and it doesn't always have to be in a physics context, is the derivative of velocity, which is the same as the second derivative of position. Is that okay? Jack's getting confused. And here's the notation for this in Leibniz notation.
Oh, I've seen that before. Where have I seen that? Sorry.
That's how you say the second derivative in Leibniz notation. And I know it looks a little funny where the twos are. If you actually think about it, this guy's thinking, I'm the derivative of y. And then this guy's thinking, I'm the second derivative of y. And that's where you see with the two, like some students would rather have the twos line up and they don't. Okay? You can have third derivatives, fourth derivatives, fifth derivatives. The third derivative in physics is called the jerk. And you can imagine maybe like the change in acceleration is what makes you jerk to a stop or jerk forward. The fourth, fifth, sixth, all those, I don't think they have physical like representations in the real world, but mathematicians certainly are interested in higher order derivatives. We're just going to really focus on the first and second derivative, so you don't have to feel like, oh my gosh, there's going to be more and more and more, and it's never ending. This is where it ends, sort of. Is that okay? Question on notation? Stretching or question?
Stretch.
Okay. All right. So far, so good? Okay. I wonder if I can do this right here. All right. Do you remember from yesterday, the days before, what does it mean for the function if the derivative is increasing? Concave up. Remember, if the derivative is increasing, that tells us about concavity. So this would tell us the function's concave up. And if the first derivative is decreasing, that would tell us its function's concave down. So here it is. How am I going to do this? Maybe I don't need to rewrite. All right, hold on. I'm going to see if I can be clever. And oftentimes I can't. All right, get rid of that. We can erase this for now. And I'm going to see if I can take this and move it over. Yeah, I would have to say it's definitely changed how I teach, how I can do notes, and how I can pass along knowledge to you. And the next step, we're going to be there in like 5 years. You'll come back to visit Shipley. You all need one of these. That's where it's going to be. And not only that, but I'll be able to you'll be able to send me what it is on your screen so I can have you work on a problem together and I can put it up and I can see what's going on all of your computers. It'll be there.
What if we screencasted ourselves during homework, then we could see what we do and what's going through our heads?
That'd be awesome. Being able to look at 30 minutes times 20 students of that'd be great. No, I'm kidding. It could be a useful tool. I wouldn't want to do it for everyone every night, but yeah, that would be great. Or actually, if we had some sort of interactive online thing where all right, so it's 7:30 and you're finished dinner and you can't do a calc problem and you bug me or something,
or
and
you can do something like that and be like, hey, can you get on? I'm gonna do this
Then you're
problem.
working.
Yeah, this is true. It's like having a.
Friends in general.
All right, so I'm going to add this, and I'm going to add this, and this completes it. So here are all the relationships that you're responsible for, and some of these you already knew. Some of them we developed today. You knew the first two, that function increasing correlates to the derivative being positive. As of yesterday, you actually knew that if the derivative was increasing, the function was concave up. But now we've added what that means about the second derivative. So if the second derivative is positive, it means the first derivative is increasing.
Then could you say that the second derivative is positive and function is concave up?
Definitely. You only need two of these to make a statement, and you're absolutely right. So Betsy says, look, we can sort of use the transitive property to say, look, that means if the second derivative is positive, the function is going to be concave up. So in essence, looking at the second derivative might be really useful at some point. I can actually think, what if we took a look at, let's see, I have to think, hold on. If the function, all right. If this is the derivative, and I asked you to draw the second derivative, is that easy or hard?
Easy.
Even though we've never really talked about the second derivative at all?
Did you just think of that as the function?
Yeah. Okay, so the second derivative is to the first derivative as the first derivative is the function. So if I want to draw the second derivative...
So it's one less.
Okay, so it's going to be a degree less. All right. The first derivative goes decreasing to increasing. So the second derivative needs to do negative, positive. It needs to have a 0 at the minimum, right? So maybe it looks something like this. That's the second derivative. Is that okay?
Sounds good.
And you could actually, I bet, guess what the original function must have looked like. Cubic. And if we draw in a cubic for our function,
This is cool.
look. Say this is.
Can you take the derivative of the derivative on your calculator and
Okay, so it's going to make your calculator think a lot, but you could do y2 is n deriv of y1, and then you can do y3 is n deriv of y2. Okay. Right? Can we look at how the red function actually, everything we would think of is true? The derivative tells us that the red function, let's see, the blue function is, sorry, why can't I think? Oh, it doesn't actually look exactly like that. I'm wrong. The red function, it's going to look cubic, and it should look like, maybe like this?
Yeah, that's it.
Because I have to have those zeros, right?
Yeah.
Whoops, I didn't even match up my zeros right.
In that area. Like general.
Wait, did I? Oh my goodness.
The zeros are at the...
At the mins or maxes, and I need to put back, no, the green. Okay. So, this should be, so the derivative goes from positive to negative, so the function should be increasing to decreasing. And now it needs to decrease, right? So far, so good. I need to continue to decrease until I get here and have a minimum, and then I'll go back. That's better. And let's look at it. The blue, or derivative, goes positive, negative, negative, positive. That means the original function needs to increase, decrease, decrease, increase. So far, so good. Let's look at the green function. The green function is the second derivative. It's negative, which means the function should be concave down. Okay? So function is concave down, and the second derivative is positive, which means the function should be concave up. It's true that when the second derivative, and Will and Gabby, I think this is what you're saying, when the second derivative is negative, the derivative needs to be decreasing. Okay? So that's a lot there, don't you think? All right? And it all makes sense, like one thing at a time, but when you take them all together, you have to build your confidence with it. You need practice. We should do practice. Ask me a question, then we'll do some practice. I'm doing all right, thanks. A little tired, but hanging in there. Yeah.
So how would you interpret this if we had a word problem?
I don't even know what that
Like,
means.
Okay, so say we're doing like what we were saying, speed. Like, say you're traveling, 5 miles.
I'm listening. Go ahead. You can try me. Like, if it doesn't make sense, I'll tell you it doesn't make sense.
Traveling, and the trip is 10 miles, and you have to travel and it's going to take you 2 hours. Then that's like the derivative would be 5 miles an hour at a certain area. So then how do you describe the second derivative in that equation? What is that? What are the units for that?
The second derivative is miles per hour squared. It's your accelerate. It's your acceleration. It's how much you're speeding up or slowing down.
Oh, okay.
Okay. Our physics students just did a lab where, let's see, they looked at the position of a falling object, and the position was parabolic, and so this was position. The velocity was linear, because the object was always speeding up. As you drop something, it's faster and faster and faster, right? And the acceleration was constant. And the acceleration was the slope of the velocity curve. And actually, they found out the acceleration hopefully was, well, you found out that it was 9.8, and we wondered why it wasn't negative 9.8. One of our questions, right? Okay. All right, let's take a look. Let's do some true-false. Yep. All right, so here we have a graph. And we want to know what's true or false about the graph. All right. F of x, the function, is positive. True or false? Who's up? Kaylee. This is, graph of f of x to the right. That's it. It is false. If it was an always, sometimes, never, you would say sometimes. But because it's not, it's false. All right, Kaylee, calling someone for B.
True.
Definitely. Increasing? Agree? All right, Will, calling someone to agree with you for letter C. Isn't if what Will said true, isn't what you're going to say have to be true? Say it. Say yes. Oh, that was so bad. If Will says it's increasing, then Liz says the derivative has to be positive. Totally agreed. All right, Liz, calling someone for D. A little harder.
True.
It is true. Let's think. The slope starts off around what? Close to
Almost 0, 0.
close to 0. Maybe it's 1. Maybe it's 5. Yeah, that's a slope that is increasing. The slope is definitely increasing. Well, guess what, Derek? That's the same as saying what, calling someone? And good. All right, so Kaylee says, look, saying that the derivative is increasing is the same as, yeah, see where I was going with that, is the same as saying, see, I was going to actually have you say true, the second derivative is positive, and then I was going to say and you were going to say concave up. But you beat me to the punch. You knew where we were going already. So concave up. That wasn't too bad, don't you think?
No, it wasn't that bad.
A little bit harder now. Okay. Not having anything to do with this graph. 15, a new question. True or false? If the derivative is positive, then the second derivative is increasing. Betsy? False. Not always. How would you change this to make it so it would be always true? Yeah, I think so. If the derivative is increasing, then the second derivative is positive. That would be true.
Can you give me an example on a graph when the derivative is positive, but the second derivative is increasing?
Okay, what is it? I have a question. Have we talked about the second derivative increasing or decreasing? Not really. We don't really have a good idea of what that means. Right? Like, we've only talked about whether it's positive or negative. So this is actually a sort of an interesting question. But so we want a graph of where the derivative is positive, okay, and the second derivative would be decreasing. This is how I would couch it to you, Liz. That's the same as asking, can you have a function that's positive and a first derivative that's increasing? Or can you give me a counterexample? So I can imagine a positive function, right, that's above the x-axis, and if the first derivative is increasing, what does that mean? What does first derivative increasing mean? Concave up. So do you agree the function's positive and concave up? Do you also agree that I could have drawn a function that's positive and a second derivative that's a first derivative that's decreasing? That would be above the x-axis, concave down. Okay? So do you see how that sort of like argument using the function and the first derivative sort of holds? Because we don't really know, what does it mean for the second derivative to increase or decrease? We don't know yet, really. Let's see. Let's do maybe one or two, and then I want to talk a little about 16. B. If the derivative is increasing, then the function is increasing. Gabby.
False.
Yeah, that's false. What should it say?
If the derivative is increasing, then the function is positive. It's concave out, concave out.
Okay. Or you could have said, I wasn't thinking of that one.
The derivative is positive for the function.
Yeah, so you could have switched either the second increasing with concave up like Gabby did, or the first increasing with positive like Betsy did. Alright, one more. If the second derivative is positive, then the function's concave up. Yeah, that seems right. They actually got it right that time. Alright. Alright. I want to talk briefly about 16 because this is like question 7, the added question on your homework. It says, F's continuous, and we're given a domain, and it's given us information to talk about this graph. On negative 5 to negative 1, it tells us that the first derivative is negative and the second derivative is positive. So what does that mean? First derivative negative means the function is... Try again. Decreasing. First derivative negative means it's decreasing. Second derivative positive means it's... Say it loud and proud. It's the function. The function is... That was good. I'm glad you called me on that. No, it was good. No, that was really good, though. Well, I'm sorry, we're not getting a... I have two people saying two different things. If the second derivative is positive, what does that tell you about the function? Go look back. Concave up. Decreasing concave up. Would you agree that looks like that, probably? Is that decreasing concave up? As a matter of fact, do you remember this from last year in pre-calc? We said there are like sort of like these four different pieces, right? Decreasing concave up, increasing concave up, increasing concave down, decreasing concave down. And when you think about it, all functions, continuous functions, are some combination of those curves. I'm going to skip this for a second and go to the next interval. From negative 1 to 2, the derivative is negative, so the function is... The second derivative is negative, so the function is... So something like that? Maybe? And can we just check back? At x equals 1... Whoops. What happened there? At x equals 1, is it true the function's decreasing because the derivative's negative? Are we going down there? And what would a second derivative being 0 be? It's a possible point of inflection. And if you look here, Zach might say, look, the concavity changed. So a point of inflection it is. All right, great. Hey, have a nice extended weekend. I'll see you on Tuesday.